Hi guys. Uh checking if everything's working. Let me see. Did it start? No, it didn't. It didn't start. Oh no, it did. Yes, all works. Okay. So, life update. I was away last week because we've been traveling and life is really hectic now, so I didn't have streams last time. But as I promised, this week we are going to have a live stream on alkenes. Yeah, that's for A-level chemistry. So what we'll do is we would write all the reactions for alkenes and preparations for A-level chemistry students. So if you're doing IB, you don't need that much information. So I wouldn't I wouldn't watch this one. But for A-level students, yes, you need that. And remember how it works. So you need to write with me. So I will be writing notes for chemical properties and preparation of alkenes. So take your notebook or an iPad and just write alongside with me. Is that all? Everything I wanted to tell? Yes, I think we just dive right in. I will also explain some mechanisms, right? But of course, you also need to know all types of like sigma and pi bonds in this topic. But remember, we're focusing on chemical properties and preparation so that by the end of the series, you would have concise reactions for all the classes of organic compounds, which would help you massively in solving synthetic pathway questions. And you will memorize it if you write it with me. Okay, so let's just dive in. Alkenes. Alkenes, can you see me? Let's just double checking. Yes, I think you should be able to see me. And we start with, so last time we did alkenes. I'll just remind myself how. Okay, so chemical properties. That's how we did it. So we did chemical properties first. Chemical properties. And the first chemical property that we would talk about is halogenation. First is halogenation. Well, alkenes, obviously, they're the substances with the double bonds, right? Which have carbon-carbon double bonds. So first property is halogenation. Let's take an ethene. And alkenes are very reactive. They react without heating, without any catalyst, with halogens, for example, bromine. And how it works is that you see you have a double bond between carbons. So what you do when they react is you're adding the molecule of halogen into the structure of an alkene. So you had a double bond, break it apart, make it single. And whatever you're attaching, in this case Br and Br, you're attaching to these carbons. Yes, you had a double bond, make it single and attach one bromine to one carbon, another bromine to another carbon. The mechanism for this reaction is electrophilic addition. Addition electrophilic. I think I wrote it with the pink. Addition electrophilic. What does it mean? It means that you don't get any side product. That's addition, right? So you're combining two molecules to get one. And electrophilic means that the bromine, like the substance, the small substance that you're adding to your organic compound, it is an electrophile, so it is attracted to a high electron density of the double bond. Well, and the official definition of electrophile, it's a lone pair or electron pair acceptor. Yes, but you can think about it as something that likes a negative charge, so electrophilic addition. And let's write it down. For symmetrical alkenes and for symmetrical molecules, everything is very straightforward. So I will write it out. Electrophilic addition mechanism. Addition electrophilic mechanism. Remember that in the questions they can ask you to write a reaction, then it's usually 1 mark and you just write that. Or if they ask you to write a mechanism, it's 2, 3, or 4 marks depending on the complexity of the mechanism. So now I'm writing the mechanism for this reaction. I will write the double bond as displayed. And I'm adding Br2 molecule, so that's BR. And let's see where the electron pairs are going. Yeah, so the mechanism is when you're showing where the electron pairs are going. Okay, so bromine molecule, it's not polar, right? Because the bond is not polar, there's only one bond, so the whole molecule is non-polar. But when it comes close to the double bond has high electron density due to the pi electrons there, and the molecule would be polarized. So the electron density of the double bond would polarize bromine molecule, and it would form a temporary dipole with delta plus on one bromine, delta minus on another. And let's see what happens. So this bond attacks Br delta plus. I will color code it. And this bond that used to be between bromines, it would leave with Br delta minus. So it's there. So what will happen is that you'll get a carbocation. So this bromine, you see this bond, it used to be a double bond between, like it used to be the bond between C's. Now these electrons are used to attach the bromine. This carbon is left without its electron, so it's a plus. And this thing is a carbocation. Yeah? So carbon with a delta plus is a carbocation. And the other bromine becomes Br minus. And this pair now is a lone pair. That's the first step. And then this pair attacks carbocation, and you form your final product. Br, Br. So that's the mechanism of electrophilic addition. Yep. Alkenes react as electrophilic addition with halogens. Through the mechanism of electrophilic addition. So if they ask you to write the mechanism, usually this easy one would be about 2 marks, but could be 3. Okay, that was the first property with the mechanism. Then yes, also about this reaction. So this reaction is a test for the double bond, yeah, to check whether your substance has double bonds or not, because bromine, it's orange, like red, orange, orange, brown, depending on the syllabus. You could have different shades of colors. And if you, let's say, if you want to find out whether your substance has a double bond, so what you can do is you can pass your substance through bromine, and if it decolorizes, then yes, your substance does have double bonds. If it doesn't decolorize, then, well, it doesn't have double bonds or triple. And if you try to react an alkane that doesn't have a double bond with bromine, you remember from the last lesson, hopefully, that you need UV light. Yeah, so it would not react in the dark. All right, next property. Next property is hydrohalogenation. So it's adding H, halogen HCl, HBr. Yes, I'll just say plus HCl or HBr. Or HI, like anything with hydrogen halides. Same thing happens, but for this reaction, let's take something non-symmetrical just to show the mechanism. So if you have a non-symmetrical alkene, let's say propene, and you add, for example, HCl, so 2 products are possible. Well, obviously you are breaking the double bond, yes, so you anyways break the double bond, you form CH3, and then the 2 different products come from the fact that you can attach H either to the first carbon at the double bond or to the second one. Well, if you attach it to the first one, then it becomes CH3 and Cl goes there, so that's 2-chloropropane. And another product that is possible, it's when you attach chlorine to the first carbon and H to the second one, so this becomes a CH2. Yeah, this is a totally different product. That's 1-chloropropane, and the first one would be the major product, so 90% of your product would be 2-chloropropane, and this would be the minor, maybe around 10% would be 1-chloropropane. There is a quick rule that's called Markovnikov's rule to find out the major product. So the general rule is that hydrogen would attach to the carbon at the double bond that already has the most H's. So you see this carbon has 2 H's, this has 1. That's why H would tend to attach to the first carbon, yeah, to form a CH3. So that's the major product. And this would be the minor when H is attached to carbon with the least amount of H's. that's just a quick way to solve this in multiple choice question, especially it's useful for AQA board. But if they ask you to explain why this is the major product, you're not allowed to mention, I mean, you can mention Markovnikov's rule, but that's not an explanation. Yeah. So to explain why this product is major, you have to write down the mechanism, and that's what we would do now. So let's explain why this is the major product and this is the minor. And I will write it out using the mechanism. So I will write this display. The mechanism, it's still electrophilic addition. Yeah, let me write it out. That's still electrophilic addition. And let's write down what happens. So this has one H, this has two H's, and I'm attaching HCl. HCl molecule is polar on its own because the bond is polar, so molecule is polar, delta plus, delta minus. Now the same thing happens as what we did before, so this bond attacks H delta plus, this pair leaves, and there are two possibilities. So first possibility, it's when, well, I break the double bond, so that bond is broken. I attach H to the first carbon. Yeah, so this bond is now here, and this is a carbocation. Yeah, that's a delta. This is the plus one, and Cl minus leaves with its lone pair now. This bond is here. Okay, that's the first possibility when I'm attaching the hydrogen to the first carbon. Now the second possibility for this reaction, it's when I attach hydrogen to the second carbon. Again, breaking the double bond. Now H goes there, and this becomes a plus. Well, and Cl minus still leaves with its pair, and this bond is here. Remember to always start the arrow on the electron pair, right? Because the arrow, what it does, it shows the movement of electron pairs. That's why if you draw it, for example, that way, that's a mistake. So you start it on the pair. And then finally, this attaches here, this attaches here, so you get two products. HHCHCl, CH3 from here, and HCH3 from there, and this is where I attach hydrogens, and this is where I attached chlorine. And remember, this is the major product. This is the minor product. All right, and now to explain why the major product is this one. So to explain the major and minor product, you have to look at the carbocation stability. So the stability of carbocation goes like this. The primary carbocations are the least stable, the tertiary are the most stable. So here, this carbocation is secondary. Why? Because the carbon with the plus is bonded to two other carbons, just like with halogen alkanes, for example, yeah? So it is a secondary carbocation. This carbocation is primary because the C with the plus is bonded to just one other carbon. And secondary carbocations are more stable than primary. Whenever I say something is more stable, it just means that it's more likely to be formed. So if secondary carbocation is more stable, it means that it is more likely to be formed than the primary one. That's why the first route is more preferable compared to the second route. Now let's explain why the secondary carbocation is more stable. In organic chemistry, whenever you have a large charge somewhere, it makes it less stable. So if you have a large charge, the substance is not stable. And if you somehow compensate for that charge, you make the substance more stable. So in the secondary carbocation, this plus, it is stabilized by the positive inductive effect from these two CH3 groups. Okay, so CH3 groups, they just tend to push electrons away from themselves. And what they do is they push electron density away from themselves towards this plus, and thus they stabilize the carbocation. In the primary carbocation, this plus is only stabilized by one alkyl group, so by one C2H5 group, which makes it less stable than the first one. Okay, so for the answer, if they ask you to explain why this is a major product, so you say that 2-chloropropane is formed via the secondary carbocation as opposed to the primary carbocation for 1-chloropropane. Then you say that a secondary carbocation is more stable because it's stabilized by electron, well, you can say positive inductive effect or electron pushing effect, something like that, of two CH3 groups as opposed to one alkyl group in the primary carbocation. That's your 3 or 4 marks explanation, and I always recommend to draw out both, because if you forget to write something in words, you can get full marks just from the from the diagrams, yeah, with the mechanism. But of course, just try to also explain why this one is more stable than that one in words. Okay, right. I'm not going to write any mechanisms, I think, anymore, because everything else would be similar, right? So if the halogen or alkane that is formed, like if the alkene is symmetrical, or the hydrogen, instead of hydrogen halide you use Br2, then it doesn't really matter. The product is always the same, so it doesn't matter which carbocation is formed first. Right. That's the second property. Okay, now I'll just fast forward, hopefully, through all other properties, and then we go to preparation. Okay, so the third property, it's when you add H2SO4. Not all boards need a reaction of alkenes with H2SO4, so check your board. AQA definitely needs it, Edexcel needs it. The rest I don't remember, so you have to double check, but even if you know this reaction, it's fine. Yes, even if you don't need it and you know one extra, I mean, you have enough brain space to keep it to keep it there. Okay, so H2SO4, you can write it as HOSO3H. For some reason they insist on that notation, yeah, so just use it like that, but it's H2SO4, you see it, right? So 2 H's, 1 S, and 4 O's. And again, of course, 2 products would be possible, right? So H can go to this C or to that C, but I will just write 1 product. But you keep in mind that you can form more. So this H goes here, that's the major product, and OSO3H goes to this one, OSO3H. The next reaction is with hydrogen plus hydrogen. Well, this reaction you know from GCSE probably. So take an alkene, add a hydrogen. The conditions for this reaction is temperature and platinum or nickel catalyst. So conditions, well, I'll write it down first and then conditions. You just form an alkane, yes? So H, again, you remove the double bond, make it single, and attach H to one carbon, H to another carbon. So you just do that. Conditions are heating, sometimes pressure, and a catalyst would be nickel or platinum. So you get an alkane. Next reaction. The next reaction is with dilute potassium manganate at room temperature. Not all boards need this reaction. Cambridge International definitely does. The rest, I think they don't, but just double check, yeah, because everything changes, and chances are when you're watching this, the video is like 5 years old. So KMNO4 dilute at room temperature. Dilute at room temperature. Well, actually, we also, yeah, no, let's do it this way. So let's do it as KMNO4, and then there are 2 different conditions. So A would be if KMNO4 is dilute and it's room temperature. And then the other conditions would be when it's concentrated and then something else happens. So dilute room temperature. If it's dilute and it's at room temperature, then what happens is you just have oxidation into a diol. Yeah, so oxygen is like the oxidizing agent, and you just form a diol. So you remove the double bond, make the bond single, and add OH and OH. um, you're allowed, usually you are allowed, if they, unless they ask something specifically to just balance it, or like write KMNO4 as KMNO4, you're allowed to write the oxidizing agent in organic chemistry as O in the square brackets, and you balance it just like you would balance normal oxygen atoms. Yes, so if you check, everything should be balanced. So you have 8 H's in total, 8 H's and 2 oxygen. So that's balanced in 3 carbons. So this is what happens. So you get a diol if you use a potassium manganate as dilute at room temperature or even cold. Yeah. But now if you are using a hot concentrated potassium manganate in acidic conditions, then depending on where the double bond is, you get different products. I'll just give you some examples. So if this is hot concentrated potassium manganate, then well, let's say if you have a double bond at the end of the chain, so the double bond will break. Okay, so the double bond breaks. I won't write it as a balanced equation. Let's just write down the products. So you break the double bond like this, and if the carbon is the edge carbon, so if it's like a CH2 group, then you get the CO2 from here. So from here you get CO2, and from here you would get an acid. So this turns into an acid. So this becomes HOOC, CH3, right? So this is oxidized. Yeah, well, that's so the double bond breaks and the pieces would oxidize into something. Yeah, so either acid or CO2, like in this case. Next one. 6 have we done with water? No. So next, but again, this I think you only need it for Cambridge, this reaction, Cambridge International, so just double check your board. Next reaction is a reaction with water. This reaction you probably remember from GCSE. It's if you have an alkene, you add water, which you can write as HOH, so you would get H bonded to one carbon, OH to another, so you get an alcohol. And conditions. Conditions would be 300 Celsius, 70 atm pressure. That's for ethene, right? For some other alcohols, the temperature may vary, but if you memorize that, it's fine. So that's 300 Celsius, 70 atm pressure, and a catalyst would be H3PO4 or H2SO4. That's the 6th property, and then the 7th. 7th chemical property is polymerization. Addition polymerization. We would also have some condensation later, yeah, but this is addition. Okay, so addition polymerization, what you do is you just like you saw that alkenes can attach a lot of things to their double bond, while they can also attach other molecules of alkenes. So if you have a substance, well, let's do first for ethene, for example. Yeah, so if you have ethene, if you take n molecules of ethene, you can add some, you can use catalyst, you could use some like change conditions and vary the properties of your polymer. But essentially what happens in a nutshell, you just break a double bond, open it up. Yeah, so you see this first carbon, it has 2 H's, so you write them up and down. The other one has also 2 H's, and you just open up the bonds on the sides. Yeah, so this double bond that like opens on the sides, and you would get a polymer with n repeat units. So this thing is called a repeat unit. So what I wrote is n repeat units. Yeah, so like n pieces would join together to form a polymer. This alkene is called a monomer. So if this is ethene, then this would be a polyethene molecule. Well, chain. It's a huge molecule. Now let's write polymerization for something slightly more complicated. So, and again, yeah, the conditions, most likely you don't need to know. For some boards, you do need to know some conditions, so you have to check which conditions you do need. But by changing the temperature, pressure, using certain catalysts, you can make, for example, low density or high density polymer, because it would affect how exactly your polymer chains are connected to each other. Now let's write polymerization for something more complicated. Let's say you have something like this: CH3, CH2, no, let's say CH, double bond C, CH3, CH2, CH3, and let's say you need to write polymerization for this alkene. So what you do is you would need to redraw it so that you only have the double bond on the line. So like I redraw it so that I have only the double bond. You see these two carbons, and then the first carbon, this one, it has H and CH3 attached, so I would write it up and down. And the second carbon at the double bond, it has CH3 and this thing attached. Yeah, so this is CH2CH3 and this is CH3. So once when you rewrite it like this, you can just remove the double bond, make it single, and open it up on the sides. And that's your repeating unit. Yeah, so your polymer would look like this. So this is one repeat unit. If they ask you to draw two repeat units, we'll just connect two pieces. Yeah, and the lines that are open on the side, I don't know, for some reason they always wanted to intercept the brackets. Yeah, so there's some convention or something, I don't know, but you lose marks if you draw it like this, for example. Yes, if you draw it like this, you lose a mark because this bond has to like go all the way through the bracket. I didn't make those rules, just accept the this game. Yeah. Okay, that's one repeat unit. So if you were to write two repeat units, well, I would write it like this. Let's write it once. So if they asked draw two repeat units for this polymer, well, you do it. This is one repeat unit and this is one more. And open it up. Yeah, not opening even for two repeat units, so you still have to keep the lines open on the sides. All right. Again, double check your board for any specific conditions. If you need to know any specific conditions, most likely you don't need, but I know the rules for when I'm doing this stream for now, but I just don't want to tell you because if you watch it later, at like in a few years, maybe the specification would change, so you have to double check. All right. This was the last chemical property, I think. Let me double check. So we did, okay, bromine we did, addition polymers we did, water we did, and sulfuric acid and HBr. Yeah, that's it. And then let's do preparation. So for preparation of alkenes, there is not much, which is good. But again, usually in the books and in the notes, you will never see preparation as a separate chapter, which is a shame because if you know both chemical properties and preparation, that would massively help you to see the connections between the classes and to solve the awful synthetic pathway questions in A2 level. Yes, like in the second A level year. Okay, so we go into preparation. First method to prepare alkenes, which we did last time, it's cracking. I forget how I put the dot, right? Yes, I do put a dot and I always forget, so that's cracking. I'm not going to explain cracking. If you want to know more about it, you can watch my alkanes stream, which was just before this one. And I just remind you that if you take a long chain alkane, let's say C12H26, and you apply temperature pressure catalyst or steam, like just watch my previous stream. So I'll just put the conditions. Temperature, pressure, maybe catalyst. Yeah, you would form a shorter alkane and alkene, and that's a random process. So if you want to have something, if you want to synthesize a specific alkene, that's not the best way to do it. Yeah, you need to have something more precise. But in general, you could just make any alkene with cracking. So you form some alkane, let's say C6H12, and we could form, for example, 3C2H4, which is ethene. Yeah, it just has to be balanced, and again, it's pretty much random. You could maybe govern the reaction to one to certain products if by changing temperature, pressure, and using specific catalysts, but normally that's very difficult to do. So if you want to have a better way of making alkenes, so a more precise way, you could use elimination of halogenoalkanes. So elimination with halogenoalkanes, right? So you start with a halogenoalkane, for example, you could have CH3. Well, let's say CBr. HCH3, and so you take a halogenoalkane and you remove HBr or HCl. So the Br would be removed from this carbon, and then H would be removed either from this one or from this one. So only it can be removed only from a neighboring carbon, so you cannot remove that H. So you remove a halogen and H from the neighboring carbon. To do this, you need to use potassium hydroxide or sodium hydroxide in ethanol. The solvent must be ethanol. If you use water as a solvent, you probably would get nucleophilic substitution, but you want to favor elimination, so that's why I would use ethanol as a solvent. And I remove Br, I remove H, so I form CH2, CH, CH3, KBr, and H2O. So think of it as removing HBr, and the HBr reacts with KOH to form KBr and H2O. All right, this is the most common way to get alkenes. Maybe there is something else. Probably you can also do dehydrogenation of alkanes, but that's not very common. So this is the most common way for synthetic pathways. All right, so I will end the stream here. If you feel like I should continue this series, please let me know. You can like the video or write a comment so that I know that that's helpful, because if you feel like it's not helpful, then I can just switch to something else, maybe solving papers or something other than that. But if you really like sitting and writing and you feel like it's helping, then let me know. All right, so next stream would probably be for IB students. We'll solve some topical questions, and then the next topic for the A-level students would be halogenoalkanes. All right, so see you next week, hopefully.